Yeah, let's get started. Okay, so somebody asked me about the midterm. So basically, the idea is to have midterm after we're talking about the analog communication, basically after the angle modulation. So it'll be a few more lectures. So it'll be either before the spring break or right after the spring break. So that'll be the time, roughly. Okay. So which one do you prefer? You want to take it before spring break or after? Before. Okay. Yeah. So if we can finish everything, then we're gonna have it before the spring break, right? If we cannot, so we have to do that after spring break. Okay. All right. So, yeah. Let's briefly review what we covered in the last lecture. So basically, why is lecture 14? I forgot to change it. It should be lecture 16. Okay, so in the last lecture, we finished talking about SSB and VSB, and we started talking about QAM, right? And so we didn't talk about application of amplitude modulation yet, and also the angle modulation. So that will be today's plan. All right, so basically for SSB, so let's review the concept, right? So for SSB, so what we claim is that if the signal is real in the time domain, so basically in the frequency, so this the signal is symmetric around the zero y-axis, right? Then, so we say, okay, so we can only transmit, so we just need to transmit half of the signal, and then we're okay, right? So this is basically the idea. And we have the concept that, so this part is called the upper sideband, and this part is called lower sideband, right? And then we either transmit this and that, or transmit this and this, right? So if you think about it, so it's kind of a little bit complicated, right? Because it is like we move the right-hand side to the right and move the left-hand side to the left, right? So it's a different procedure for this. So this is called SSB. And so we have two cases as we claimed, right? So we have upper sideband and lower sideband modulations. So, and here is a image to illustrate our concept, right? Okay, and so in order to get the for example, USB signal, right? So basically, what we need is to get rid of the other half, right? How to get rid of the other half is via the Hilbert transform, right? It's a convolution between the message signal and 1/πt, right? So this is a Hilbert transform. So in the frequency domain, so what we do is just multiply the signal by a unit step function, right? In the frequency domain. Okay, and here are some properties of this 1/πt, right? If we do a Fourier transform, so this will be the form, right? And then if we write it clearly, so this would be what this signal means, right? So if we plot it, right, because it's a complex signal, right? When we plot it, we cannot use only one figure, so we have to use two figures. One is the magnitude, and the other one is the phase, right? So for the magnitude, it keeps the same, right? We don't do any changes here, but for the phase, so it's a phase shifter, right? It's an ideal phase shifter, so below 0, we shift it by pi/2, and if f is bigger than 0, we shift it by minus pi/2, right? It's an ideal phase shifter. Okay, and for the SSB signal, so this is this is basically what we do, right? So what we do is that we transmit it with we transmit the signal with a DSB-SC modulator, right? And for the other part, we need to cancel that. So what we do is that we multiply the signal by a still by a DSB-SC modulator, but instead we're doing this with sine modulation, right? Okay, and after this, so we add them together, so we get SSB signal, right? And so before this, we need to get this Hilbert transform of it. Okay, so by the Hilbert transformation, so it's like we do a frequency shift by pi/2 in the frequency domain, right? That's why it was written there. Okay, so this is basically the SSB signal. Okay, Oh, and for the SSB demodulation, so basically what we tried is a very intuitive, coherent demodulation. So what we do is that we use the signal, multiply the cosine 2 pi fct, right? That's it. And then we get rid of all the high frequency components, and then we can get the original m of t, right? So we went through the math in the class. So if you have any questions, just take a look at the lecture notes. Okay, and then we say that because the SSB is kind of ideal, right? So it gets exact half of the signal in the frequency domain, right? So which is, which is hard in practice because, so in practice, it's always hard to get this sharp transition in the frequency domain, right? So we say, okay, we cannot get it. So what do we do with that? So we call that VSB, right? So for VSB is that so we can have this like a more smooth transition period in the frequency domain, right? So we have some leftovers, right? So vestigial basically means some leftovers, right? So then we need to deal with, so therefore in terms of the transmission, it'll be much easier, right? Because it's more smooth, right? It's not like a sharp transition, right? But for the demodulation, it'll be harder. So basically, what we do for the demodulation is that we design a filter such that when we shift this to this side and shift this to this side, so which is basically how we demodulate it, and then the signal, the original signal will be recovered, right? So we design two filters such that this can happen, right? One is the filter to get this. The other one is the low-pass filter in the end, right? The low-pass filter in the end will not be the ideal low-pass filter, so that will be designed based on, the filter to get this this signal. Okay, yeah, it's a little bit more complicated, but it's important to understand conceptually how we can do this, right? Okay, and this is the diagram of VSB. So basically, if you look at the book, so the V naught and the VHI, it somehow have this inverse operation, right? Not exactly. V0 is the inverse of HI, so it's related to the inverse of HI. Okay, and okay, so next we just introduced quadrature amplitude modulation in our last lecture. So basically, the idea is that for the SBSC or AM signal, right? So so the the disadvantage of those kind of signal is that it does not have the bandwidth efficiency, right? It sort of have the double bandwidth, right? But for the SSB, so we have the advantage of the bandwidth, right? Because we just use half of the bandwidth, right? But the disadvantage for SSB is that we need coherent demodulation, right? So which is relatively hard. But for the AM signal, right? So we introduced two demodulations, right? So one is square demodulation, and the other one is the rectifier envelope demodulation, right? So it does not require the coherent demodulation, so which is good. Okay, yeah. Okay, so now let's say, okay, is that possible that we can have the advantages of the easy demodulation? Meanwhile, so we can have the same bandwidth efficiency for SSB. Okay, so is that be possible? So basically, yeah, maybe I'll write it here. So if we recall for example, our USB signal, so that is MT cosine 2 pi FCT, right? That's basically the DSB SC signal, and then we minus MH of t times sine 2 pi FCT, right? So this MH is the Hilbert transform, right? So now the idea is that, okay, so this part is completely wasted, right? So this part is used to cancel the other half of the signal here, right, in the frequency domain, right? It's completely wasted. So now how about we change this idea, right? So instead of transmitting this guy, so we transmit a new message here, right? If we claim this is M1, how about we transmit another message here, right? In this way, so we transmit two messages, okay, but the bandwidth is also doubled, okay? Because this will not cancel the other half of it, right? Bandwidth doubled, but now we're transmitting 2 messages instead of 1. So the bandwidth efficiency will be exactly the same, okay? So now the question is, so this is our transmitted signal for QAM, QAM, okay? Now the question is that possible to demodulate this kind of signal? Or how can we demodulate that, right? Okay, and we're gonna cover that in this class. Okay, so in this class, firstly, we're gonna finish talking about QAM very briefly. And then we're going to talk some applications of amplitude modulation. And then we're done with amplitude modulation, right? Okay, then we're going to introduce the next modulation approach, which is called angle modulation. Okay, so this is our agenda. Okay, let's continue on this. So basically, the first one is QAM. All right. Okay, for QAM modulated signal, as we said, so basically the form will be almost identical as this single sideband modulation, but the difference is that now instead of transmitting one signal, we're transmitting 2 signals. Okay, so that's a form of QAM. Okay, and for this one, so this is called, let me see, this is called in-phase component. Or normally we say that's the I part, okay? And this part is called the quadrature component. Or we call that the Q part. So we're not going to talk about a lot of this here, but for the digital communication, we're going to focus a lot on this QAM modulation. Okay, later on you're going to see, so this part basically corresponding the real part of a signal, and this part corresponding to the imaginary part of signal, right? When we think about the transmitted signal as a complex function instead of real function. Okay, great. And so this is a basic concept. So now let's take a look at the modulation diagram, right? So it'll be almost identical as SSB, but we don't have the Hilbert transform here, right? So which can be easier. So the diagram would be almost identical as before. So basically what we do here is that we have M1T, and here we have M2T, right? For M1T, so basically we're just going to draw a DSB-SC modulation, right? So basically we multiply a cosine, this 2 pi of CT here, right? Or 2 pi, or omega C of omega CT. Okay, so for the other part, so we need to multiply here a sine, right? So in order to get a sine, so basically what we do is that, so for this cosine, we shift it by minus pi over 2 to get a sine, 2 pi of CT, right? And then we're going to add them together. So then we can get our SQAM signal. Okay. So that's how we do this. Okay. Great. So this is the modulation part, right? So how about demodulation? Right? What do you think? So how can we do demodulation? Right? So now we need to get 2 signals out, right? Instead of 1, right? I have M1 and M2, right? So now we didn't learn anything else, right? So basically, all the we only learn like 3 demodulation approach, right? The first one is coherent demodulation. We multiply everything by a cosine, right? And then we learn the square demodulation for AM, and we learn the amplitude demodulation for AM as well, right? Clearly here, so we can now use the square and the envelope demodulation, right? So probably we're gonna try the first one. That makes sense, right? Let's say, okay, so what if we multiply this by cosine, right? So what if we multiply this by a cosine 2 pi of ct? Will that work? Let's say, so if we multiply this, what is going to happen, right? So this multiply that. Yeah, let's forget it for now, right? Yeah, what we're most familiar is for this part, right? So if this multiply that, and if we ignore this part, assume that is 0, so can we do the demodulation? We can, right? That's the SBSC exactly, right? We just pass the signal. If we don't have this, we just pass the signal through a low-pass filter, and that's it, right? Okay. So now let's say, so what if, so if we don't have this, okay, and this part is okay, if multiply cosine, okay, how about if we say we multiply sine instead of cosine? Right, and let's assume now, so this part doesn't matter anymore, okay? We only care about this part. Will that work with the same idea? Yes, it will, right? It's a sine square. So can you, yeah, let's write it as omega c, it'll be easier. Right, it's a sine square, right? Do you know the trig identity of sine square? Yeah, I think I know it, but let me make sure. Yeah, so basically it will be almost identical as before. So what we do is that it's 2 1 minus cosine 2 omega c t instead of plus. Okay, and by the same idea, right? So this is basically the higher frequency component. We can get rid of it, and then we can know this part if we don't have this, right? And that'll be the demodulation. Okay, so now the only thing we need to check is that whether this multiply this will be gone, or this multiply cosine would be gone, right? So that is the thing that we're going to verify. Okay. So basically, what we need to check is as follows, right? So we need to make sure whether the inner product between this and M2T sine okay, so the only thing we need to check is as long as this is 0, then we're okay. Okay, so now let's check whether it is 0 now. So basically, in order to compute it, so now it's to compute the inner product in the time domain, right? So we claim it may be hard, then we convert that to the frequency domain, okay? So let's compute that in the frequency domain. So what is the Fourier transform of that? Here in terms of M1. So M1 times cosine, right?
It's like 1/2 M1 of F minus omega c, or FC, F minus FC.
Yes.
1/2 M F plus FC.
Very good, right? So, and similarly, what is the Fourier transform of this guy? Right, it's a sine, right? So remember, so we need to write down the Fourier transform of sine, right? So Fourier transform of sine, yeah, it's nothing but we have 1 over 2j, and then j omega ct minus e minus j omega ct. Right, difference here is that we have 2j instead of 2, and then we have a minus instead of plus, right, in this way. So now we do the same thing for this signal. So basically what we're going to have is that half is here's M1, right? So M2 2j F minus Fc minus 1 over 2j F2 and plus Fc. Right, here we need to be a little bit more careful, right? So for this guy, for in the time domain, it's a phase shift by this amount. In the frequency, it'll be a minus here, right? So be careful on this, right? So this, so now we just need to compute the inner product between this and that, right? So now we have this is like 2 terms here and 2 terms here. So overall, we're going to have 4 terms, right? So let's write down all the 4 terms. So so eventually, yeah, let's see. So we take this 1 over 2 and 1 over 2j out. We have 1 over 4j here, right? Then we have 4 inner product, right? For the first one, we have this and that. So we write M1 F minus Fc and M2 F minus Fc, right? And similarly, we're going to have this and that, right? So this is minus M1 F plus Fc, M2 F minus F plus Fc. Okay, so then we have the cross term, right? So we have this and that and this and that. Okay, so basically it's minus M1 F minus Fc and M2 F plus Fc and plus M1 F plus Fc and M2 F minus Fc. Okay, very good. Right, so this is basically the inner product. Now let's verify the value of it. Right, so first the easy part is for this and that. Right, how about this? So do you know the value of this and that? Right, remember definition, right? So this, for example, this equals to the integral of f1 f minus fc times m2 f plus fc conjugate df. Right, so this is the definition of inner product. Right, if you do this, what's the value of it? Yeah, maybe I'm not clear enough, right? So let's assume the signal look like this, right? So let's assume the signal have similar bandwidth, or let's see. So this is M1F, and this is our M2F, right? Like this. And then if we shift this, to 2 sides, I shift this to 2 sides, and then multiply them together, right? Think about it. Then can you tell me what's the value of it? Yeah.
0 because there's not overlap.
Yeah, exactly, right? So I've seen this many times, right? So that should be 0. Any question on this? So everybody can see this? Yeah, if you don't, just ask, right? So I can tell you how we compute it again. And similarly, for this one, it'll be 0 again, right? Because there's no overlap, right? This is on the right, this is on the left, right? Then multiply them, it'll be 0. Okay, so now the question is, how about this and that? Right? How can we figure out these two? Right, they're on the same side, right? So that's definitely not 0. Okay, and similarly for this one, it's not definitely not 0. Okay, can you think how we can figure out those? Or figure out the value of this together? Right, again, look at this figure, right? So if we shift M1 and M2, both of them to the right, so what we're going to get is basically, I say this is M1F, and so this is our M2F, oh, minus, sorry, should be minus FC, here is minus FC, right? So now we compute the inner product between this and that. And also we subtract the inner product between the same thing, but on the left-hand side, right? Exact same thing, right? So would that be the same? Right, so this is corresponding to this, right? And for this, it's like we have exactly the same thing, but on the other side. So this is M1 F plus FC. Then we have another one is M2 F plus FC. Right, the inner product between this and that will be the same as the inner product between this and that. Yeah, right, they are exactly the same thing, right? So what you do is that you just move everything to the middle, right? And both of them would be the same as the inner product between this. Let's say here's M1F and M2F, right? Up to some scaling, right? Right, if you move this and that, to here, I think the scaling would be like maybe 1/4, right? There will have some scaling here, right? So then they will be the same, right? If you really want, we can compute it, right? So basically, again, so the definition of it is nothing but M1 F minus FC times M2 conjugate F minus FC dF, right? So when we do this integral, so what we do is that we let F prime equals to this guy, F minus FC, right? And then we have M1 F prime, M2 F prime, and dF prime, right? Right. This is nothing but the inner product between M1F and M2F. Right. Similarly, we can get the same thing here, right? And then we can see this and that are equal. Then they canceled. Okay. Eventually, so the entire thing would equals to 0. Okay. And now we verify this equal to 0. So basically, it means that so this signal and this signal are orthogonal, right? If they're orthogonal, right, so there will be some way, to separate them. Okay. So we're gonna see that in another form when we talk about digital communication, probably. So yeah, we're not going to talk about derive it exactly here, but you just need to understand, they're orthogonal. So look, so we didn't have any constraint for M1T and M2T, right? They can be any signal, right? They're orthogonal. So then we're good. Right, that clear? Any questions? Good? Yeah, just let me know if you have any questions. Okay. All right. Okay, so that is, need to move to this one. Okay, so now let's briefly talk a little bit on the applications of AM, right? So we know, communication started from analog communication, right? So before the digital communication that we use every day today. Okay, so here we focus on three main applications of the amplitude modulation. So the first one is the AM broadcast radio, and the second one is the analog TV, and the third one is the analog telephony. Okay. So let's see for this AM broadcast radio. I think that we still use that today, right? So there are some AM base stations here in Gainesville as well, right? I think in your lab, so you should see signals from there. Okay, and for the audio signal, so basically normally the signal bandwidth is less than 10K hertz, and so basically in order to transmit, it means that we need 20K hertz for the bandwidth, right? Because we double that. And so for the carrier frequency, so we have from 540K to 1,700K. Okay, and in 10K hertz increments, right? And we have 4 classes in terms of the power, right? The highest power is 50 watts, and the lowest power is 0.25K watts. Okay, and so they're like A, B, C, D, and the power of it is decreasing. Okay, and so for the signal, so basically we have different characteristics during the day and night, right? So during night, it's easier for transmission. So it basically means that, so I think it because, so the signal can bounce off the ionosphere, right? And what happens is that, so during night, we may want to use a lower power for transmission, okay, for the AM radio signal. Right, so if you want to see more details, you can check this website. Okay, and as I said, right, so there is an AM base station here in Gainesville. So it's located at this 75th Street and Southwest 8th Avenue. So anybody see that? So you can write down this. You can take a look at that today. So if you want, right? The signal. So this is the AM A850. It's called AM 850. So basically, it means that the frequency is, the frequency is 850 kilohertz. Okay. And if you compute the wavelengths for that, remember, so the wavelength is speed of light divided by the frequency, right? So basically, we have, so this is the length of the signal, wavelengths of the signal, okay, which is very large. Okay, so that is a brief look at the AM radio. And now for the analog TV, so this is much more interesting and much more complicated, right? For the radio, we know just use AM. AM basically means the DSB signal with the carrier, right? When we say AM, okay? So for the US analog TV, it almost uses everything we talk about today, right? So basically, for the TV signal, it's a video signal. It's very complicated, right? So I have 3 kinds of signal here. The first signal is the luminance, right? Like black and white TV, right? Without color, okay? And the second signal is what? The color signal, right? And then the third signal is what? For the video, we need color, we need, yeah.
Audio.
Say again?
Audio.
Audio, exactly, right? So we have audio as well, right? So normally what we do here is that we need to transmit them separately, okay? So we allocate a bandwidth for audio, we allocate bandwidth for luminance, and we allocate bandwidth for color. That's ideal, right? But in practice, let's see what we do here. Okay, so here basically the bandwidth of a video signal, black and white, is 4.2 megahertz, right? So this is basically the width of our signal, right? Meaning, this is the width of the signal, okay? yeah. So, and then we need to add audio onto it, right? And then the total bandwidth is 4.6 megahertz. Okay, and so in order to transmit that, so basically we use USB and USB and LSB, right? So now this is kind of interesting. So it's not a symmetric decomposition, right? So for the USB signal, so we have a higher number, and for the LSB signal, we basically have a lower number, right? So because it's VSB, right? Remember that for VSB, we need to transmit a little bit higher, right? For this width, it's like 4.5, but for VSB, we transmit 6 in total, okay? So it's a 1/4, it's not 1/4, it's like 1/3 wider compared to the original signal, right? Does that make sense? Okay, and then for the color, so basically what we use is kind of very interesting. Let's see whether that makes sense or not, right? So it's a combination of QAM and the VSB. Does that make sense? So remember that, right? The reason we have QAM is that we want the same efficiency as VSB or SSB, right? But it doesn't stop us, for each, because the signal we transmit still like this, right? We transmit like twice as this kind of thing, but still can use half of them to transmit, right? So remember for this one we have M1, it's a DSBSC, and for this guy, right? If we replace this by M2, right? Let's write M2 here. So if we replace this guy by M2, right, and this will become a QAM. Okay, and similarly, so this one will be more or less very similar to this one in the frequency domain, right? Then we can still use half of it to transmit. It's be more complicated, right? We could combine them, right? So this is what is happening here, right? We combine QAM and VSB, right? Or so basically, for QAM we have I and Q, right? For I channel we use VSB to, and again, so this is not a symmetric, decomposition. So we have 1.5 and 5, and we'll have, the other way, right? 1.5 here and not the other way, sorry. So yeah, we have 1.5 and 1. For Q channel it's just DSBSC, and for I channel it's VSB, right? So they have different numbers here. I think it's because of the sensitivity of our eyes, right? I don't recall exactly, but for the I channel, Q channel, they transmit different colors, right? So because our eye have different sensitivity to different colors, so for some color we want to transmit more information. For some colors, we may want to transmit less information, right? That's how it works. And here's a figure on how, what the signal look like in the frequency domain, right? So overall, we have 6 megahertz. Right, and here's the audio, and here are the video, right? It turns out that, so what we do is that, so this black thing, so that's the luminance, right? Black and white, and this is the color. You can see they overlapped, right? We'll add this on that, okay? So basically, it depends on the channel characteristic, the signal characteristics. It turns out that, these two can be transmitted, and they do interfere with each other, but it can be handled. Okay, so that's how it transmits, right? Kind of interesting. And so for this, it's kind of, combine everything we have learned so far, right? We have QAM, we have VSB, right? We have the DSBSC, and so on, right? Very nice. Any questions? Right, and here is the carrier frequency, right? So the signal that we look at is in the baseband. It's a regional signal, right? In order to transmit it, we need to shift it into a higher frequency, right? Now we have 2 bands here to use. One is a very high frequency, and the other one is ultra high frequency, right? Use these 2 kind of carrier to transmit in the US. But unfortunately, I think now we don't have this anymore. I think it's defunctioned. Right now, everything is digital, so we don't have an analog TV anymore. And the other thing, the other application of amplitude modulation is long distance telephony. So yeah, for this one, I just want to emphasize one thing. So because it's only speech, right? So basically, the bandwidth here we transmit is only 4K, right? So when we talk about digital communication, where we can see that because our voice is only 4K hertz, for the bandwidth, right? We only need like 8K to sample it to maintain the information. All right, so here the important thing here is that we do the division, or maybe let's see. So we do multiplexing in this case, right? So for the TV, so we do multiplexing between the color signal and the luminance signal, right? But here we do multiplexing among users, right? It basically means that for telephone, it's easy to understand. Different users can talk at the same time, right? Right. So basically, so this is called multiplexing, right? So multiple users can share a single channel, and how it's going to share in this case is called frequency division multiplexing. So this basically means that one user occupy a frequency band, and for different users they do not overlap. So that's basically what we're using today for 4G and 5G. Right? The difference here is that they somehow overlap, and we can handle that. Right? This one is strictly they don't overlap. Okay, so it's called FDM, and so it looks like this. So basically, this is one user. This is in the frequency domain, right? And this is another user, another one, so on, right? And what we do here for the modulation is just multiply a different cosine here, right, to make it shift into a different place, and then transmit. Okay, and then we have a lot of voice channel here. For example, we have different kind of grouping techniques, right? So originally we have like 12 users grouped into one group, and then 5 of them, it's not 6, 5 of them group into a super group. Now we have 60, and 10 of them will group into another group. It's a 600 voices, right? And so we have different devices here to handle them, right? This is how it works in practice. And and this is the details of the grouping, and you can take a look at this. It's called L carrier. Okay. And I think that'll be it. Great. Yeah, those are very simple, brief overview of the applications of amplitude modulation. Right? Any questions? Right, we have 5 minutes left. Then we can have a brief introduction on the on the angle modulation. Right. So okay, so let's see why we need angle modulation. Right. So for the amplitude modulation, so can you imagine what kind of the disadvantage of it, right? The only reason that we need another modulation is that there's something in amplitude modulation that we don't like, right? So what we don't like in amplitude modulation? Power efficiency, yeah, that's only for AM, right? Yeah, for DSP, SC, I think is better. Yeah, but it's a good point, right? Power efficiency is sometimes it's not very good. Any other reasons? Yeah, it's not extremely easy to think about, right? So basically, yeah, let's recall let's recall the definition of DSP-SC, right? So basically, let's see, for DSP-SC, for this signal, so what we do is just this, right? Right, so this is our message, okay? So in other words, right, so we draw this a few times. So basically, ideally, yeah, let's say the signal looks like this, and then the modulated signal looks like this, right? And then we have carrier, okay? So it basically means that, we modulate the signal directly on the amplitude of the carrier, right? So in practice, when we transmit that, we're going to have some noise, right? The signal will not be like this, okay? So in practice, the signal will be like, there will be lots of variations here, okay? And when we do the demodulation, so we're going to get back of the red one, not the black one, right? So if there's any noise, it will be directly added on the signal, So that is not what we like. Okay, so what we like is that, okay, if there's some noise, then it's better to not have it, or there's some way to deal with it. For the AM signal, we don't have a much way to deal with it because it's just on the, on the amplitude, and then, when we do the demodulation, we just get back of the red one, right? And the other thing is that, when we increase the bandwidth, it may not help too much to get rid of this kind of noise. Okay, so it basically means that, okay, so can we think about another kind of signal that we can better deal with the noise? Okay, and then we start thinking about the carrier, right? Because we need to have the carrier, right? The carrier is a signal that can move the signal to different band, different frequency point, right? We definitely need the carrier, right? So the idea is that, okay, is that possible that we can change what is inside of the carrier to help us to carry the information? Would that be possible? Okay, so that's basically the idea of the angle modulation, right? So the signal is not directly dependent on MT, but dependent, but there's some dependence there. Okay, so this would be the advantage of the angle modulation, but the disadvantage is that, as you may think about, right? So for the DSP-SC, it's very easy to do demodulation, but for if something happened here, it may not be direct, very easy to do the demodulation. Okay, we need more complex circuit. Okay, now, yeah, I'll spend 1 more minute. So now let's introduce some notation here. So yeah, let theta t be the angle. Okay, yeah, angle is basically something inside, right? Sometimes we call that as another name, right? So what we call that normally?
Phase.
Yes, call that phase. Okay, so let this be the angle of a modulated carrier. Okay, I'll spend 2 more minutes. Yeah, if you can leave if you are urgent. Yeah, I started late for 2 minutes. Okay, and say then, and angle modulated signal can be written as, so we use notation like this, means angle, right? As angle t is A multiply the theta t. Okay, A is just a constant. Okay, so next we're going to take a look at the relation between frequency and the phase, right? So phase is basically the value of theta t, right? Then what is the frequency? Okay, so basically, yeah, let's see. Normally, for a signal, so we know if it's a carrier, so that will be like this, right? That will be a carrier. Okay, and this is our frequency, and the phase is the entire thing, right? In this case, theta t would be equals to omega c times t, right? So in general, can you tell me what is the relationship between the phase or the angle and the frequency? Right, so in this phase, that's exactly the relationship, right? The phase multiplied time would be equal, the frequency multiplied time equal to the phase. right? So, but in general, the relationship is as follows. The frequency is the derivative of the phase. Okay. So that's basically the relationship, right? So next lecture, we're going to take a deeper look at this and introduce you the frequency modulation and the phase modulation. Okay, that makes sense? Yeah, that'll be it for today. Thank you.